There are a couple of topics I want to discuss through here with the items that we'll be working in Chapter 3. There are certain kinds of equations and circumstances that tend to arise over and over and over again. And just to make sure we have those ideas sort of solidified in our mind, I want to go through a few examples and a few techniques and a few procedures that maybe you know, maybe you might not know quite so well. And I think if we have these, that's going to assist us as we go through working with the first derivative analysis, the second derivative analysis, finding the max mins, all these issues we're going to be dealing with in Chapter 3. They're based upon some sort of foundational material that isn't strictly speaking calculus, although some of it is a little bit. And so I want to sort of talk through a few of those notions here. The first is something very basic that dates back probably to your days in basic algebra somewhere. That has to do with how do you solve if you have a fraction equal to 0. Now this arises very often when we're doing the first derivative analysis, the second derivative analysis. This arises very often because when we use the quotient rule to find the derivative itself will be a fraction. And then when you want to find the type 1 critical values, you set that derivative, you set that fraction equal to 0, and then you solve. And so this sort of a circumstance naturally arises in this procedure. And so I want to make sure that we understand this process, not just how to do the process, but there actually are a few sort of short versions or techniques we can use to expedite this process. The big thing to bear in mind is this. Anytime you have a fraction equal to 0, no matter how simple or no matter how complex the circumstance, if you have a fraction equal to 0, the very nature of that statement means you have a numerator divided by denominator. I'll represent it as numerator divided by denominator is equal to 0. Anytime you have a fraction equal to 0, that very statement means you have this circumstance. So these are logically equivalent. This and this mean essentially the same thing. Now the question is, how do you solve that? Well, to solve an equation like this, you have a single fraction equal to, well, it's not a single fraction, but it is now. So anytime you have a fraction equal to 0, at the very least, mentally, even if you don't need to do it physically, think of this as being 0 over 1. 6 is 6 over 1. 9 is 9 over 1. 28 is 28 over 1. 0 is 0 over 1. And now you have a single fraction equals a single fraction. You may cross multiply and set them equal. But when you cross multiply, the same thing happens every time. When you cross multiply, you are always, because of the nature of this setup, you are always going to get numerator times 1, and that is always going to be numerator. And that's going to equal, because of the setup, you're always going to get denominator times 0. And no matter what the denominator is, anything times 0 is 0. And so, setting a fraction equal to 0 is logically equivalent to setting the numerator equal to 0. And so, let's suppose you're trying to solve. For some reason, you're working through a problem, you're working, and you generate x minus 5 over x squared minus 9. And that's your derivative. And so you want to set that equal to 0. You want to solve that equation. The net effect, once you see it, you don't need to go through this process every time. It's going to be the same every time. The net effect is this. If you have a fraction equal to 0, essentially, you may ignore the denominator. If you have a fraction equal to 0, that corresponds to setting the numerator equal to 0. which is to say, in this case, if I have x minus 5 over x squared minus 9 equal to 0, you may immediately say that implies that x minus 5 is equal to 0. It's actually more than that, but it's at least that. And then from that, we get x equals 5. All right? So setting a fraction equal to 0 means set the numerator equal to 0 and solve, because the denominator gets vanished in this cross multiply process. All right? Another piece to bear in mind. Suppose you're working along, and you get 6 over x minus 4 equal to 0. Well, you set the numerator equal to 0. But if I set 6 equal to 0, remember, if there is no variable, there will be no solution. If there is no variable, there will be no solution. So this gives no solution. Now, one of the things that happens very often in basic algebra is students get the wrong idea. And you need to get rid of this idea. You need to take this idea, rip it out of your brain, and throw it away forever. Students get the idea that no solution. Remember when you solved all those equations back in basic algebra? You solve. You work. You do a page and a half of work, and you get no solution. And you think, well, that was a big waste of my time. You need to take that idea and throw it away. You need to take that idea and get rid of it. No solution does not mean the same thing as wasted time. Listen to me. No solution does not mean you wasted your time. No solution is a piece of information that you did not have before you started. No solution means this. Here it is. Get ready to write it down. Pause the video if you need to. Here it comes. No solution means, here it is. Wait for it. No solution means whatever you're looking for, there isn't one. Because if there had been, you'd have found it. No solution means whatever you're looking for, there isn't one. If you're looking for type 1 critical values and you get no solution, that does not mean wasted time. It means there are no type 1 critical values. That's a piece of information you didn't have before you started. I mean, remember way back when? Way back in basic algebra, you had an equation. Oh, remember doing this? You had an equation for this line and an equation for this line, and you're trying to find the point where the two lines cross. Remember doing this? And you work, and you got no solution. And you thought, well, that was pretty stupid. Take that idea and throw it away. No solution means whatever you're looking for, there isn't one. It does not mean the same thing as no information. When you're trying to find the point where two lines cross and you get no solution, what that means is there is no point where the two lines cross. What do we call two lines that don't intersect? We call them parallel lines. That's a piece of information you didn't have before you started. And so no solution means whatever you're looking for, there isn't one. That's why I'm having you write down every time, and you stinking better write it down every time. If you want full credit on the exam, you better write down type 1 critical value, and then you find them. And then type 2, you go find them. If you're trying to find a type 1 critical value, see, you set the fraction to 0, which means you set the numerator to 0, and you get no solution. If there is no variable, there's no solution. What that means is there are no type 1 critical values. If you're trying to find type 2 critical values and you set up an equation and you solve, and you get no solution, that means there are no type 2 critical values. So no solution means whatever you're looking for, there isn't one. So here we go. Suppose we have f of x is equal to 6 over x plus 3. And I'm going to say, find the derivative and find all the type 1 and type 2 critical values. Find all the type 1 and type 2 critical values. Let's just do that part of the problem. If you were doing the actual first derivative analysis, you'd do more with it. But let's just find all the type 1 and type 2 critical values. So we're going to find the derivative. That's denominator times the derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator, well, that's just 1, all over the denominator squared. And let's simplify that a little bit because we're going to try to solve this. We're going to set this to 0. This falls out. So what we end up with is negative 6 over x plus 3 quantity squared. And if I want to find the critical values, I'm going to find the type 1. I'm telling you, if you want to get full credit out of me, then you stinking better write this down. If you don't write this down, I don't care if you find a way to travel to Mars in 3 days. If you don't write this down, you're not getting full credit out of me. Type 1. This is where the derivative is equal to 0. And so this is where we have negative 6 over x plus 3 squared is equal to 0. Now, using our rule, if a fraction equals 0, that's the same thing as setting the numerator equal to 0. Here, I'll do it down here. So that implies the numerator is equal to 0. But if there is no variable, that means there is no solution, which means there are no type 1 critical values. There are none. How do I know there are none? Because that work verifies there are no type 1 critical values. Type 2 critical values. All right, so now that goes back to our topic from before. If we have a fraction, if I want to set this fraction equal to 0 and solve, that's the same thing as setting the numerator to 0. But if I want to find where is this fraction undefined, where is this fraction undefined, where I want to find type 2 critical values, that's where this derivative does not exist. Does not exist means it's undefined. It means it has no value. Where does this function, where does this fraction fail to exist? A fraction fails to exist anywhere the denominator is equal to 0. So if you want to find where the fraction does not exist, you set the denominator equal to 0. And so that's the moral of the story. If the derivative is a fraction, anytime you do the quotient rule, it turns out if you can use the quotient rule, it makes things a little easier. Because anytime you use the quotient rule and your derivative is a single fraction to find the type 1 critical values, you set the numerator to 0. To find the type 2 critical values, you set the denominator equal to 0. I say again, if the derivative is a single fraction, if that's not the case, all bets are off. You have to do some other work. But if the derivative is a single fraction, then to find the type 1 critical values, you set the numerator equal to 0. To find the type 2 critical values, you set the denominator equal to 0, which in this case is x plus 3, quantity squared equals 0, and you solve that. Type 1, numerator equals 0. Type 2, denominator equals 0. And it turns out we take the square root of both sides. So we get x plus 3 is equal to 0. And that implies, subtract the 3 across, we get x equals negative 3. And then you would go merrily along your little way with whatever problem you're working with. But that's the notion. If the derivative is a fraction, type 1 critical values, set numerator equal to 0. Type 2 critical values, set denominator equal to 0. That's going to be the same no matter if you're trying to find absolute extrema or you're working a first derivative analysis or a second derivative analysis, whatever you're working on, anytime, anywhere. A fraction, if you're trying to find the type 1 critical values, set the numerator equal to 0. Find the type 2 critical values, set the denominator equal to 0. So that's the first of our background topics, is working with this fraction. A single fraction is the derivative. Anytime, even if it's not a derivative, anytime, any course, any class, anywhere. If you have a fraction equal to 0, that's numerator equal to 0. If you have a fraction where it's undefined, a fraction's undefined if the denominator is equal to 0. So that's our first background topic, and I hope you're going to get some mileage out of that as you go through the homework. We have a few other topics that's going to be talked about in the next couple videos.